All right.
Like you turn it down the driveway and they're like, shoot.
Okay, let's get started. We are on lecture 17. We are rocking and rolling. We are, that should be shear and moment diagrams 2, not 1, because we did that last time, so I'm going to change that. That's going to bug me. Okay, how did homework 5.1 go? I'm hoping it was kind of easy, maybe a little tedious. Did homework 5, did anybody have any major challenges with 5.1? Okay, good. All right. So today what we're going to do is we're going to develop our graphical approach for drawing shear and moment diagrams, and you'll find that it is much easier than what we did in the last homework, and on top of that, you can still get answers from the last homework using this approach. So to make the point, in class last time, we did this example. We had, let me pull this up. All right, so in class, this was the example that we did last time. And we said, okay, let's cut a section and look to the left or to the right. It doesn't really matter. And regardless of which way that you look, we got an internal shear of 15.8 kips and an internal moment of 309.6. And it didn't matter if you were looking to the left or looking to the right, those were the answers that we got. Well, I propose that we can get these same answers with our graphical approach, but instead of getting the shears and moments just at one point, we can get the shears and moments at any point, okay? So it's a lot faster, it's a lot easier, and we get more info out of it at the end of the day. So why wouldn't we do it, okay? So let's go into this. Now, if you remember, we spent the lecture last time, we did our internal shear and moment calculation, and then we arrived at this. We did a short little derivation, and we got to this point where we had recognized that if you have shear and you differentiate it, you'll get the loads, or really the flip side is a little more useful, that if we have the loads and we integrate those loads, we get the shears. And likewise, for between shear and moment, if we have the shears and we integrate those, we get the moments. Now, I know that when structural analysis students sometimes see the fractions with the D's and the wiggly little S's, they go, no. I don't want to do calculus. I want to avoid calculus. The wiggly little S's, I've hit my limit with all this calculus. That was a joke, not a very funny one. What we're going to do is, instead of directly applying these derivatives and integrals, we are going to use them as useful guides. Now, there is one application in a little bit. I think we're doing that on Wednesday. We're actually taking the derivatives and integrals. Not only is it easy, but it does actually serve as a check. I don't want to get too far down the rabbit hole, but that we'll find that's a pretty useful application when we're dealing with triangular loads. We'll get to that later. Now we've got load, shears, and moments, but I want to take those load, shears, and moments and develop a simple means of constructing shear and moment diagrams. So the way this is going to work is we're going to start off with our free body diagram, or our diagram that contains all of our loads, and then we'll try and develop a relationship between load and shear. So I propose that based on our expressions, that at any given point, whatever the slope of the shear diagram is, that's going to be equal to whatever the loads are present on that beam at that point. And I propose that between any 2 points, the change in shear is equal to the magnitude of load between those 2 points. And where am I getting these? I'm just getting these really from taking these expressions and reading them, right? It's like this first expression, the derivative of shear with respect to x is w. So what I'm saying is that at any given point, whatever the slope of the shear diagram is, it's equal to the load. If I've got between 2 points, the magnitude of the load between those 2 points is equal to the shear. So, I mean, I'm not really, it's not really mysterious where I'm coming up with these conclusions. And I can do the same thing between shears and moments. At any given point, the slope of the moment diagram is equal to the shear, and between 2 points, the change in moment is equal to the area under the shear diagram. Again, nothing really there that's really that far of a stretch. One point I will mention is that when we did our derivation, I was looking at this sort of arbitrary distributed load. You could do the same derivation for concentrated moments or concentrated loads as well. I'm not doing that in here. I think you kind of get the point. But the best way of exploring this is to actually apply it. Okay. So what I'm going to do is hopefully this is starting to become a theme in this class, is that whenever we introduce a topic, we start easy and then we start, ramping it up in difficulty a little bit, one at a time. And we're going to do that with this topic as well. And we're going to start with shear and moment diagrams for beams that are subjected to concentrated forces. Okay? So we're going to cultivate our graphical approach by looking at concentrated forces because they're really easy from a mathematical perspective. Whenever you have a beam that is subjected to a series of concentrated forces, between those concentrated forces, assuming there's nothing else on it, between those concentrated forces, the load is zero. Okay? So if the load is zero, let's go back to those polynomial integrals that we talked about. So if you have the number zero, and you take that zero and you integrate it, you get a constant function. And if you take a constant function and you integrate that, you get a linear function. Okay? So whenever we're looking at a sort of a given region in a beam like this with a concentrated force, where the integral is constant, the shear diagram is a series of constant function plots. And what does the graph of a constant function look like? It's just a horizontal line, right? So shear diagrams for concentrated forces sort of have this like stair-step look to them. So a constant, constant, constant. And however much we jump is equal to the magnitude of the force at that point in question. So we have a constant, let's say V1 here, a constant V2 here with zero slope. And then when we integrate that, what we get is a piecewise linear function for the moment diagram. And again, there's a lot of info packed in here. So for example, we have a linear function here, a linear function here. What is the slope right here? What is the slope of this line? The slope of this line is equal to the magnitude of that shear. What is the slope of this line? Equal to the magnitude of that shear. Okay? So there's a lot of really, really good info just packed into a shear and moment diagram that makes the construction of them really, really easy to do. Now what we're going to do, we are going to need to integrate. We're going to need to integrate the shear diagram to compute the moment diagram. But if you go back to top one, what is integration? Integration is just determining the area under a curve, and we're dealing with rectangles. So I don't know about you, but I really don't need to break out calculus 2 methods of integration to determine the area of a rectangle. I can just do length times width. So while we're integrating, we don't need to apply calculus 1 or calculus 2 techniques of integration. It makes our life a lot easier. Sound good? Okay, so what we're going to do is we're going to draw the shear and moment diagrams for this beam. And I have a theme also in this class where I sort of like to reuse examples a little bit because I want to start with values that we're familiar with and expand upon them. So we're going to draw the shear and moment diagrams for this beam. And I again just want to illustrate that we've already looked at this beam a couple of times. The first time we looked at it, we computed the support reactions and we got 32.2 for BY and 35.8 for AY. We also did this example in class on Wednesday, and we said, okay, let's samurai sword or lightsaber right here at x equals 12 feet from A, and let's compute the internal shear and the internal moment at that point. And we got these values right here. Okay, we got a positive shear and a positive moment. So let's see if we actually get those when we construct the shear and moment diagrams graphically. Okay. Now, one thing I haven't emphasized yet, but I think may become kind of clear after today, and that is that shear and moment diagrams, and really this unit in the class as a whole, is a portion of the class that really lends itself to having a straight edge with you. Okay, so having a straight edge would be kind of nice, and I think everybody here has a straight edge because, like, here's my ID. It's a straight edge. So I mean, everybody's got some sort of means of drawing a straight line. I sort of think it makes construction of these diagrams a little faster, and I'm all about doing the work as fast as possible. So I just throw that out there, that if you have a straight edge, bringing it to class might help a little bit. Okay, so I'm going to show you how I go about constructing shear moment diagrams. So I'm going to scroll this down a little bit. What I like to do is I like to keep my shear and moment diagrams sort of lined up and organized so that when I'm referring upwards and downwards, I'm looking at the same thing. So what I like to do is I like to draw these guidelines. So I'm going to draw these like these green dashed lines. I guess that's not totally necessary, but I really like doing this because it's easy to follow when you start referring up and down. Okay, so we're going to draw these guidelines up and down. There's no real hard and fast rule as to how many of them that you draw, but usually what I like to do is put one for every concentrated force, every reaction, and any place where a load starts and stops. And you'll see as I do that, throughout the semester. Okay. So we have our, what I'll call our load diagram. So if I ever use the term load diagram, the load diagram and just the original free body, that's essentially the same thing. The first thing I'm going to do is I go from the load diagram, I'm going to construct the shear diagram. Now the way that I like to do that is, so I'll start out, I will put, let's just do a solid flat line like this, okay? And what I like to do is instead of putting units all over the place on the shear diagram, what I like to do is put a little label out here. We'll say this is the shear diagram, and we'll say that everything that's in the shear diagram is in kips. So any number that I sort of draw inside the shear diagram that isn't a dimension, I'll know that it's in kips. The other thing I like to do, and I probably don't need to do this here on the screen, but you might want to do it if you're using a pencil, is I like to put these little tick marks. So I'm going to do them like this. And the reason I like to do that is because it indicates that this is like the zero line, because our shear diagram is going to go above the line and below the line and above and below and whatnot. And I like to have an indication that there is a zero, sort of a baseline. And if you notice, my tick marks are sort of drawn like arrows, like they're going from the left pointing to the right. To be honest, that's not really necessary for beams because I'm always going to draw shear diagrams from here going this way. But for frames, when you've got members at all different orientations, I kind of think it's nice to know which way you're drawing the shear and moment diagram. So I sort of get into the habit of putting these tick marks to indicate that that's the zero line, and then indicating that we're going this way. Okay, sound good? All right, is everybody set up with me, or do you need a minute? Okay, all right. Okay, so what we're going to do is we're going to start out at the very left. We're going to start out over here at 0, okay? And the idea is that with a shear diagram, what we're going to be doing is plotting the change in vertical forces from the left side of the beam all the way over to the right side of the beam. And the idea is that if you've done all of your statics correctly, you should start at 0 and end at 0, because that will just be a verification that the sum of the forces in the y direction equals 0, okay? Now, what you do when you draw a shear diagram is you basically just do what the beam tells you to do. So for example, at the very beginning of the beam, I start at 0 and I see at the very beginning of the beam there's this 35.8 kip load pointing upwards. So the beam is saying, hey Greg, go up 35.8. I say, okay, beam, I'm at 0, I'm going to go up 35.8. Because apparently in my head the beam's talking to me. So I start at 0 and I jump up to 35.8. And I'm trying to keep things to some reasonable scale. So like, for example, if this is like 30, maybe like that's 40, maybe that's 15, I'm trying to keep it to some reasonable scale. But as long as, it doesn't have to be perfect, as long as you label it appropriately, you're good. Okay, so let's continue on. So I'm at the very beginning of the beam, and the beam tells me to go up 35.8, and then I start going from left to right. So I'm at 35.8. So what is the beam telling me to do from here to here? And the answer is nothing. There's nothing on the beam from here to here. So if there's nothing, what I do is I just keep on walking. I just keep on walking, keep on walking, keep on walking. And then I get right here, okay? And I get right here, and the beam says, hey, Greg, you're at 35.8, go down 20. So I'm at 35.8, I go down 20. What am I going to be at? There we go, 15.8. So we'll call this 35.8. Jump down. We'll call that 15.8. Can you all read that in the back? And I'm writing kind of time. Okay, all right. So what do I see from here on out? I see nothing. 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 Boom. Okay, I'm right here. Okay, so I'm still at 15.8. Nothing's changed. I'm at 15.8. And then the beam tells me you need to go down 30, Greg. I say, okay, well, I'm at 15.8. If I'm at 15.8 and I drop down 30, what am I going to be at?
Negative 14.2.
I'm going to drop down negative. I'm going to drop down negative 14.2. That's 100% right. So I drop down. That's probably about like that. Call that, negative 14.2. Negative 14.2. And then I go over, 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 bam, I'm right here. So I'm at negative 14.2. I drop down 18. What does that put me at?
Negative 32.2.
There we go. And I think we can probably see where this is going because I got nothing, 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 bam. I'm right here, I'm at negative 32.2. I jump up 32.2, and that brings me back to 0. Okay. All right. And so that, ladies and gentlemen, that's your shear diagram right there. That's it. Okay. Now I want to take a step back and see, was that hard? That's pretty easy, right? One of the nice things about a shear diagram is that it has a way of confirming, both shear diagrams and moment diagrams, I should say, they have a way of confirming that your support reactions are in fact correct. So I just told you that 35.8 and 32.2 are the reactions. Now granted, we did this problem a little earlier in the semester, but let's say we had. Let's say that I just told you, and I just said, trust me, these are right. Well, how can you confirm that I'm right without applying equations of equilibrium? Well, one way is to draw the shear diagram and the moment diagram. Because I started at 0, and I go up, and go down, go over, and I end back at 0. And so what that tells me is that those two reactions at least satisfy sum of forces in the y direction being equal to 0, because I started at 0 and I ended at 0. The only way to ensure that they totally meet equations of equilibrium without applying them is to draw the moment diagram, which we'll do here in a bit. All right. Does that idea kind of make sense? So it serves as a check for you. Okay. All right. Now, in order to construct our next diagram, which is the moment diagram, we need to look at this again. So if you use the load diagram to construct the shear diagram, you use the shear diagram to construct the moment diagram. And what we're doing is we're integrating. Okay, so in order to do this, I need to integrate this shear diagram. And so the way that I'm going to do that is I'm going to compute the areas of these rectangles. So we'll call this rectangle 1, 2, 3, 4. And I'm just splitting it up into these segments, you know, here, 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 and here. And what we're going to do is we're going to compute the area under these given rectangles. So let's see what we get. So let's do this over here. Let's take our time with it. So let's look at the area of 1. So I propose the area of 1. I'm going to call it positive because it's above above the y or the x-axis, and it's 35.8 kips. So notice how the height is in kips, and the width. What's the width of that rectangle going to be?
6 feet.
6 feet. Okay, that's interesting. So if I compute the area, the units are going to be in foot kip. The area of the shear diagram, the units are in moments. They're in foot kip. So that's something to think about. What is 35.8 times 6?
214.8.
214.8. Do I have a second?
Yeah.
So 214.8 foot kips. And let's do the same thing for area 2. So that's also going to be positive because it's above the axis, and that's 15.8 kips times a width of 9 feet. And so what is 15.8 times 9?
142.2.
142.2 foot kips. Okay, now for the third one, I'm going to call that negative because it's below the axis, so we'll call it 14.2 kips times 7 feet. And so that's negative. What is that? What is 14.2 times 7?
99.4.
99.4. And then foot kips. And then area 4 is negative 32.2 times 8 foot. And what is that?
257.6.
257.6. Sound good? Now, here's something you can do right now. What do you get if you sum those areas? What do you get if you sum this, and this?
0.
You get 0, okay? Why do you get 0? Because the sum of the moments are 0. That's what this is. We are integrating the shear diagram to construct a moment diagram. The sum of the moments are 0, right? Now, I'm going to forewarn you, there are some scenarios where when you sum these areas, you don't get 0. And there is a very specific scenario when that happens. It's whenever you have concentrated moments. Because if you have concentrated moments, they don't show up on your shear diagram. So, for example, if you sum up the areas and you get 60, I bet you there's a 60-foot kip moment on that beam. So that's sort of where that's going on. Or you have an error in your calculation. So it could be that too. Okay. All right. So far, so good? So now what we're going to do is we're going to construct our moment diagram. So I'm going to trace these dashed lines down a little bit further. Okay. And I'm going to do the same thing I did before. So I'm going to draw a flat horizontal line. I'm going to put some tick marks on it. We're going to do our moment diagram. We'll do it in blue and say, so this is our moment diagram. And like I said, just with shear diagrams, again, same thing with equilibrium, we start at 0 and we end at 0. Okay. Now what I want you to think about is I want you to think about integrals and polynomials. So if I have a constant function and I integrate a constant function, I get a linear function, okay? So I propose that if we're talking about this first region, I have a constant function and I integrate that, and I get a linear function. Now, so I propose that's a linear function, okay? Now if I start at 0, how much do you think I go up? How much do I go up, do you think?
214.8.
214.8. I come up the amount of that integral. In fact, maybe what I ought to do is I ought to say, let's put these areas here. Let's put those areas right there, just so we have them there. So we go up to 214.8. So far, so good? Now here's a pop quiz for you. What is the slope of that line? You don't need to do any math. What is it?
35.8.
35.8. Why? Because that's the value of the shear diagram. The slope of this line is 35.8. That's the slope of that line. So now what do? We do the same thing that we did with shear diagrams to get to the moment diagram. We're just looking at areas. So I start at 214.8. What do I do from here to here? I go up 142.2. So if I'm at 214.8 and I go up 142.2, what am I at?
357.
357.0. and it is also linear. What is the slope of that line?
Fifteen point eight.
There we go. So think about this from graphing. Let's go back to algebra. So remember, positive slopes go up like this, right? So this is a positive slope, this is a positive slope, but it's less of a positive slope. It's not going up as intensely, right? Positive slope, less positive slope. What about from here to here? I drop down. How much do I drop down?
99.4.
So if I'm at 357.0 and I drop down 99.4, what do I get to?
257.6.
And if I'm at 257.6, that's going to drop me down to 0. So we've got, we've got that, which is 257.6. That goes down to 0. And now look at our slopes. Now we're starting to go downhill, so our slopes are negative. What's the slope of this line? It's negative 14.2. So a negative downhill slope. This one right here, negative slope, and it's negative 32.2. And again, equilibrium was satisfied because we started at 0 and ended at 0. And I propose the only way that that would work is if those two reactions that we computed, those were the only two values, 35.8 for A and 32.2 for B. Those are the only two that we could use that would satisfy both vertical force equilibrium and moment equilibrium, illustrated graphically with the shear and moment diagram. Does that make sense? All right, does anybody have any questions so far? So this seems pretty easy, right? Now let me show you something. Let's go to that. This is what we did last time. We said that if we cut a section 12 foot from the left support, we get 15.8 for shear, 309.6 for moment. Does this tell us the same thing? Well, let's see. Okay, so we go 12 feet from A, so we're about like that. So that's section 1-1, where this is 6 feet. Okay, so let's chop that samurai sword very, very far down. All right, what happens here? That's the shear diagram. What do we get on the shear diagram? 15.8. What do we get? So is that what we got before? Yeah, that's what we got before, right? So that's exactly what we got before, okay? But is that what we get on the moment diagram? Well, it looks like it. I think it looks like it. Let's see. So, like my sound goes. Okay, so we get this. Can we verify that that is in fact the value that we're interested in? Well, let's see. So internal shear and moment at x equals 12 feet. So what I'll say is by observation, V is plus 15.8 kips. Okay, that's pretty easy. Now what about the moment? Now I propose for the moment there's two different ways that we could do this. I'm going to show you the second way here in a bit. Let's look at the first way. So I'm going to sort of zoom in on that section of the moment diagram. And so what we've got is we've got a value here of 214.8. We got a value here of 357.0. We're sort of interested in that. Now we know the slope of that line is 15.8. And we know that this dimension, what is that dimension? 6 feet. So if I want the moment at section 1-1, a simple way of doing this, remember, slope, here let's just make sure we're all clear on this, slope is just change in y over change in x. So if you want the change in y, just take slope times the change in x. So if you want, we can say 214.8 foot kips plus the slope is 15.8 kips times the change in x of 6 feet. And what do we get? Should get 309.6, do we? There we go. Now that is one way to determine the internal moment at a particular point. There's another way, another means, and that is to integrate the shear diagram. And here's what I mean by that. Okay? So if I take a samurai sword or lightsaber through the shear diagram, so what I'm going to do is I'm going to take a samurai sword or lightsaber through the shear diagram, and I'm going to look to the left. Okay? So let's kind of see what that looks like. So if I do that, I've got, so here's the shear diagram, actually. Here's the shear diagram. And I start off at 0. I jump up to 35.8 over. Then I drop down. And then I drop over. And then it's like right here that I cut the section. Like that's where I samurai sorted, right? And so this dimension here was 6 feet, and this one was 6 feet as well. Do you see what I'm doing? So all I'm doing is I'm just, I'm going here, samurai sorting, and I'm just drawing all of this. And so I get this image. Would that be a fair statement? So let me ask you a question. What is that area? How do we compute that area? Would it be 35.8 times 6 feet plus 15.8 times 6 feet? What is that?
309.6.
By golly gosh gee. Kind of crazy, isn't it? But the cool thing about the graphical approach is now we have a shared moment diagram everywhere. We can do this instead of having to cut sections and write equations of equilibrium. This is just like linear interpolation and looking at a picture, The picture also gives us a gut check. Like for example, if we had computed this, like just as an example, okay? So if we had computed, let's say we did this by hand with equations of equilibrium and we got like 409.6, would that answer really make sense? I would say no, because this is 214.8, this is 357, the answer's got to be between that. So if you got 409, it's like something's wrong, So it gives you a means of correcting and checking your math with a nice pretty picture, so, which is, I kind of like that. So, all right, let me take a step back. How are we doing? Any questions so far? Okay. All right, so what we're going to do next time, let me see what time it is. Oh, we're doing good on time. So what we're going to do next time, I'm going to talk a little bit about what we're going to do next time, but we're not going to get into the example. So, because we're rocking and rolling on time. I know it's Friday, but I will let you out a little early. But I want to at least introduce what we're going to talk about on Monday. So what we're going to do next time is we're going to look at distributed loads. Okay, and concentrated loads and distributed loads. It's just the next sort of step step up on the polynomial ladder. So when we have a distributed load, what happens is this. So we have a load that is constant, okay? When we have a load that's constant and we integrate that, we have a linear function for the shear diagram. So what will happen, like for example, if we're looking at this region, we'll go from a high shear, let's say, to a low shear, okay? And that high shear to that low shear, what we can do is compute the area under the shear diagram. And again, we've got to compute the area under the shear diagram, but no need for intervals, because that's just rectangles and triangles. So no need for the wiggly little S's, okay? And what we can do is plot the moment diagram. Now, if we have a constant shear, we have a linear, constant load, linear shear, we have a quadratic moment diagram, a parabola. And how does the graphics work? Well, if we go from a high shear to a low shear, we go from a high slope to a low slope, okay? So that's going to be our means by which we construct shear and moment diagrams. And just like next time, we're going to have an example that we go off of. Now, with this example, I'm actually going to have us do start to finish. I'm going to have us compute the reactions too, because I want you to see how it goes from start to finish. I want you to see how these reactions feed into the analysis as a whole. Before we get to that problem though, we're gonna do this on Monday. I want to do a slight geometry problem for you. I've been doing this a long time, and what I found is that the actual construction of the shear and moment diagram, that concept's easy. It's stuff like this that ends up tripping you up. So we're gonna do a quick little geometry problem on Monday, and then we're gonna ramp it up in difficulty. And then, like I said, we just keep doing this. We do with triangular loads and then internal hinges, concentrated moments, all that jazz, but we just start easy and work our way up. Sound good? Would you like 12 minutes of your life back? Okay, all right. I'm gonna stop record. I'm gonna pull the code up again if you missed it. That's all I got. I will see you all on Monday.